FH divides the diameter GI of the circle with centre O as shown, where the distance of F to J is 2, the distance of J to H is 7.5, and the distance of O to J is 1. Find the radius of the circle. Now, we proved in an earlier video that if two chords of a circle intersect inside the circle, then if we multiply this distance by this distance, we get the same result when we multiply this times this. Now, I'm going to call the radius of the circle R. So what's the distance of G to J? Well, it's just R plus 1. What's the distance of I to J? Well, the distance of I to O is the radius of the circle. So IO is equal to R. So that means the distance of I to J must be R minus 1. Distance of O to J is 1. So this distance here is R minus 1. Another way we could arrive at that is to realize that IJ is the diameter of a circle. So if we add R plus 1 onto R minus 1, we should get the diameter. Well, we get R plus R, that's 2R, and 2R is the length of the diameter of a circle. The diameter is twice the radius. So I just applied the theorem. If we multiply the two green lengths together, that is R minus 1 times R plus 1, we must get the product of the red lengths. That's 2 times 7.5. So we just have to solve this equation to find R. Now if you multiply R minus 1 by R plus 1, you'll get R squared minus 1. The cross terms will cancel out. You get plus R minus R. Sorry, you get plus R squared plus R minus R minus 1. The plus R minus R's cancel out. 2 times 7.5 is 15. So this very nicely works out to R squared equals 16, from which we get R equals 4. Of course we get minus 4 as well, but that's not a legitimate answer in this case. We're dealing with lengths of lines, so we have to have positive values. So this distance here must be 4 plus 1, which is 5, and this distance here is 4 minus 1, which is 3. 5 3s are 15. S is a circle with centre O, AB, AC and EF are tangents to the circle. So there's AB, there's AC, there's EF. AGO is a straight line. So G is the point of intersection of tangent EF and the circle. Write down angles AGE and AGF. Well, here is angle AGE. AG is one arm, GE is the other arm. AGF is this angle here next to it. Well, this is straightforward because we're given that EF is a tangent to the circle, and we know that a line from the center of a circle to the point of contact of the tangent to the circle is perpendicular to the tangent. So both of these angles are 90 degrees. Prove that triangles AOC and ABO are congruent. So here's triangle AOC. Here's ABO. Now, OC is a line drawn from the center of the circle to the point of contact of this tangent. C is meant to be the point of contact. And we know that such a line is perpendicular to the tangent. Similarly here. So we have that both of these triangles are right angle triangles. So we have one angle that's the same. Now what else is the same about these two triangles? Well, they have a side in common. This side AO is the same in both triangles. So we have an angle that's the same and we have a side that's the same. Okay, so AO is a common side. You can just state the tangent property for the reason that both of these triangles are right angled. Now, we also have that the distance of O to C is the radius of the circle. We can call it R. But that's the same as the distance of O to B. O to B is another radius. So we have another side that's the same. Distance of O to C equals the distance of O to B. Just put equals R. So we have two sides and an angle that are the same. Unfortunately, the angle is not in between the two sides. See, the angle would have to the angle would have to be between the two sides that are the same. If we want to use side angle side, we can't do that here. The angle that's the same is right angle, and we haven't proven that these two are equal. Or we haven't proven that these two are equal. What we can do is use Pythagoras Theorem. So by Pythagoras Theorem, if I call this side small a, this side small r, and the hypotenuse small h, then we know that the sum of the squares of the two short sides of a right angled triangle, that is a squared plus r squared, equals the square of the longest side, h squared. So we can rearrange this to get a squared. A squared must be just r squared minus... Actually, it's the other way around, sorry. It's h squared minus r squared. So there's a. Now, the other triangle is also right angled. I'm going to call this side small b for convenience. This side small r, and small h is the side that's common to both triangles. And we see that b squared plus r squared equals h squared. So we can rearrange this to get b squared equals h squared minus r squared. So we can see that both a squared and b squared are equal to the same thing, namely h squared minus r squared. So we can conclude from this that a squared equals b squared, which means of course that a equals b. So we've proven that a equals b. So not only are sides of length h and r the same in both triangles, but these two sides are the same. So I could call this one a, it's a units long. So we see that in both of these triangles all three sides are the same. These two sides are the same, and of course this side is the same in both, so put 3 dashes on it. So we can use the side property. We don't even have to use this property here. Well, actually we do need this, because that's how we can apply Pythagoras Theorem. Okay, it's just that we don't need to refer to angles as part of the congruence, as one of the congruency properties. We don't have to see what angles are the same. We only need to show that these are right angles so that we can apply Pythagoras here to prove that the sides are the same in both triangles. So that property is abbreviated SSS. The three sides are the same. Both triangles are congruent. If the three sides are the same, everything else is the same about the triangles. The angles are the same. So the two triangles are congruent, and we want to deduce that angle CAO equals angle OAB. CAO is this angle here. So we wanted to deduce that this angle is equal to OAB. OAB is this angle here. Now, I'll call this angle X, use a capital letter for an angle, and this angle Y. Now, what can we say about X and Y? Well, they're both opposite equal sides in the two triangles. They're both opposite the side of length R. So these two sides are corresponding sides in the two congruent triangles. So that means that these two angles are equal angles in the congruent triangles. So I'm going to call the angles X and Y. You can revert to calling them CAO and OAB if you like, it doesn't matter. Since X and Y are both opposite the side of length R in both triangles, and since both triangles are congruent, we conclude that angle X equals angle Y. So these two are equal angles in the congruent triangles. Of course, another pair of equal angles are these two here. The sides corresponding to both of these angles are this side here and this side here, and these are equal, as we've shown from Pythagoras. Prove that triangles AGE and AGF are congruent. Well, G is meant to be the point of contact of this line to the circle. So this line is a tangent, and you know, as we saw earlier, these angles are both 90 degrees. So these two triangles are right angled triangles. You can see that they have a side in common, which I'll call H. This H is of course different from the previous H. Now, from the previous part, we know that these two angles are the same. I call these angles X and Y, and I might as well call them X and Y here. Now this is important. Without this fact, we don't have enough information to prove that these two triangles are congruent. Now we have a case of two angles the same and a side the same in both of these triangles. So anyway, I'll just go through the proof. X equals y from the previous part, as I said already. Both triangles are right angled. Well, that's just a tangent property. This line is a tangent, as I've explained before. Also, H is a common side in both triangles. That's this red line here. So we see that two angles and a side are the same in both triangles. That's the angle side angle condition for two triangles to be congruent. So two angles and a side the same. Actually, it doesn't matter which side is the same. If two angles and a side, any of the sides are the same, then the triangles are congruent. So these two triangles are congruent, so everything about them is the same. So obviously we've already shown that x equals y and these two are angles are the same, so the remaining angles must be the same. So these two angles must be the same. Now what sides are the same? Well, it's pretty clear what sides are the same. It's pretty clear that EG equals GF just from this picture. But just to be more precise about it, the sides that are the same are the corresponding sides. That is, the sides that are opposite the equal angles. So both of these angles are the same. I'll do them in green. Both of these angles are the same, so the sides corresponding to these angles are the sides that are opposite these angles. So these must be a pair of equal sides. Oops, gone too far, sorry about that. So if you want to write down this deduction, you need to say that side EG and FG are opposite equal angles x and y. So that means that these sides are corresponding sides, and we're dealing with congruent triangles, not similar triangles. So it means that the corresponding sides are equal. Well, actually these two triangles are similar triangles, but we're dealing with more than just similar triangles. If we're just talking about similar triangles, then we'd be looking at the ratio of the two corresponding sides. Ratios of corresponding sides would be the same. But in the case of congruent triangles, corresponding sides are equal. The radius of the circle is 9 centimeters. Find the area of the triangle OFA if the distance between A and F is 7.5. So here is triangle OFA. So let's take 7.5 as base. Well, if 7.5 is base, to get the perpendicular height, we would have to extend the base and drop a perpendicular from this point. But look, the perpendicular height of this triangle is actually the radius of the circle. Perpendicular height is 9. Because we know that the line from the center of the circle to the point of contact of a tangent to a circle is perpendicular to the tangent. So this is also the perpendicular height of triangle OFA. So the area is half the base, so take 7.5 as base, times the perpendicular height, which is 9. That comes to 33.75 centimeters squared.